Okay, welcome back. We are moving on to finding a different type of transformation right now in the next two examples. So we've done our horizontal shifts, we've done our vertical shifts, and not in that order either. We did the vertical shifts first, then we did the horizontal shifts, and now we're going to do something a little bit different. So again, we're going to graph each function, and we're going to describe how the common function is moved to create this function that we're graphing. Okay, two things. We're going to graph and describe. So right here we have q of x equals the square root of negative x. So what is your common function that's being manipulated? And I think it's pretty obvious. You see the square root sign, okay? So we're looking at y equals the square root of x. And you should know what that looks like. We've done that already here. The square root of x function looks like this. It takes off kind of fast. It's got a good rate of increase as we take off, but then it tapers out, putters out a little bit. Continues to increase, just takes a long time in order to increase. All right, so there's your absolute value of x function. Now I know what most of you are thinking. You're probably toying with the idea that you see a negative under your square root function. And you're thinking you can't have a negative under the square root function. And that is true. You cannot have the value of your radicand be negative. So I'm just going to toy with this domain for a minute here. I'm going to write q of x equals the square root of negative x. And if this is my radicand, which is under square root sign, which is an even root, this radicand is not allowed to be negative. So it must be greater than or equal to 0. We've done a whole quiz on that, so I think everybody's okay with that idea. Negative x is greater than or equal to 0. Well, if negative x is greater than or equal to 0, I want to know what x is. So if we change the sign of the x from a negative to a positive, we're going to have to change the sign of 0, which has no sign, so it stays 0. But the inequality symbol has to change as well. So basically, I'm dividing by -1, divide by -1. Negative divided by negative is a positive. 0 divided by -1 is still 0. And the inequality symbol turns around. I'll talk to you for just a minute as to why that's true, and then we'll get back into graphing. But I just want to talk about this concept for a moment. If I have a number line, and 0's right here, if I have the number, let's say, 2 and 5, isn't it true that 2 is less than 5? I would hope you'd say yes. And you know what? I think I'll spin it around just because this example says greater than first. So I'm going to say, isn't it true that 5 is greater than 2? And again, I hope you say yes, because 5 is to the right of 2 on your number line, and that's a definition of greater than. When you plot the numbers on the number line, whatever number's to the right is greater than whatever's number's on the left. So 5 is greater than 2. So if I negate this 5, and I negate this 2 by dividing by negatives, I get -5 and -2, but where do they fall on the number line? If I look at -2, I'm over here. If I look at -5, I'm over here. Now how does -5 compare now to -2? -5 is to the left of -2. So the inequality symbol has to turn around if you jump to the other side of 0 on your number line. Because having a 5 on the right side of 0 compares it to a 2 by making it greater. But having a 5 on the left side of 0 makes it a -5. It makes it less, not greater. So numbers change on the other side of 0. And it's because of the minus sign. All right, so enough of that. Let's just get back. All right. This tells me that the x value itself is going to be negative. So if the x value itself is negative, and then I negate it again, my radicand becomes positive. If the variable itself is represented by, if the number itself is represented by this x, this number itself has got to be less than or equal to 0. So it could be like -1, or -2, or -3, or -4. And then when you take this x value, and you put a negative sign against it, like if x happens to equal -4, well then negative x would be a positive 4. Let's see how we show that. So when you see the negative attached to the radicand, I'm not saying that the thing underneath my square root symbol or my radicand is negative. I'm saying that the radicand is not allowed to be negative, so therefore the x itself, whatever number I plug in for x, has to be a negative number to begin with, so that I can negate it and actually do the problem. So let's start, and you'll see what I'm talking about a little bit more as we work examples. Okay, I want to graph this sucker. So I'm going to start over here with my mapping, and I'm going to say g of q of x, is the square root of negative x. Now I want to pick a number. I'm going to pick a 0, and if I negate 0, I get 0, and I take the square root of 0, and I still have 0. So 0, 0 is definitely a point on my graph. Now if I pick a 1, and I put a 1 in here, I get the square root of negative 1. And that's not allowed in the set of real numbers, because square root of negative 1 is your I, which is an imaginary number. And again, the x and the y-axis are real numbers, so I have no way of plotting that. So according to the set of real numbers, 1 is not in the domain of this function. Can't do it. So let's try negative 1. When I put a negative 1 in for x, it would look like that. The negative sign would be here, and the x itself is negative 1, which gives me the square root of 1, which is 1. So negative 1, 1. Negative 1, 1. What other numbers should I plug into my domain? Plug into my function, have in my domain. How about if I tried a negative 2? This would give me, and I should write q of negative 2 equals the square root of negative 2. And again, oh, no, I lost my negative sign, didn't I? Okay, so forget again. This gives me the square root of 2, which is about 1.4, and I don't feel like playing with it, so I'm not going to use it. I decide not to pick that point. What would be a nice point to pick that I could put inside my set of parentheses right there as my input? And what I'm hoping you're telling me is negative 4. If I put q of negative 4, when I negate my negative 4, that gives me 4. You can say negate negative 4, or you can say the opposite of negative 4. Either way, you're going to come up with 4. The square root of 4 is 2. So negative 4 comma 2. Here's 1, 2, 3, 4, 1, 2. Negative 4, 2. Now let's not forget that this function here, this q of x function, has got to kind of look like this y equals the square root of x with something happening to it. So does it look like we're shifting up and down or left and right? And I hope you say no, it doesn't. And I hope you can kind of see that this is going to take off just like that. Y equals the square root of x took off, except it's going to go in the other direction. And that's what is happening with this function here. The next number I would like to plug in maybe might be negative 9. So when I take q of negative 9, it gives me the opposite of negative 9, gives me the square root of 9, which is 3. So negative 9, comma 3 would be way over here. Let me see, all the way up there. So I'm choosing not to do that one either. I got my 3 points, but I have an idea what's happening. And it takes me all the way over here to go all the way to negative 9 before I go up another unit. So that's weird. Here, in order to go up a unit, I only had to go left 1. In order to go up a unit between this 1 and this 2, I had to go left 3. Next time I'd have to go left 5. Next time left 7, left 9, left 11. I have to keep going left and left and left more and more and more just to go up 1 unit. So that's my square root of negative x function. Now I need to describe it somehow. And you guys tell me, or I'll tell you, how this function is manipulated to become your q of x function. I'm hoping you see it. You simply just reflect that original common function over the what? Over the y-axis. You reflect over the y-axis, and it shows up over here. So q of x equals the square root of negative x is y equals the square root of x reflected. I'm going to put a word in here because if I'm reflecting over the y-axis, I'm going to leave a word. I'm going to leave a space for a word right here, and I'm going to say over the y-axis. But what is the path that each of these points take? The original function is over here, right? So this point right here, which was what, 4, 2, becomes negative 4, 2 when you reflect 4, 2 over the y-axis. So what's the path of this point? What's a good word that I can use to describe the path of that point as it, and then probably a little bit high there, okay? As this point moves from here over to here, isn't it moving horizontally? And that's what I really want to hear you say. Reflect it horizontally over the y-axis. That's going to give you a little bit of a pause, because when you hear y-axis, you don't want to think horizontally. You want to think vertically. Well, if you're reflecting over the y-axis, you're moving horizontally. Period. You are being reflected over the vertical axis, but your movement of the points are horizontal movements. So when you reflect over the y-axis, it is a horizontal reflection. It's kind of weird, but it's true. Kind of weird, but it's true. When you reflect horizontally over the y-axis, all of your positive x's become negative and all your negative x's become positive, which we haven't done an example that way, but this is it for the other direction. So I don't really want this 4, 2 here, and then I want this circled here. Let's go ahead and box this answer. If time permits, at the end of this video, I'll do another example just like this for you and help you out a little bit. Question 6 gives me, what is this? R of x is equal to negative x squared. So my common function that I'm playing with, a lot of teachers call common functions parent functions. It's almost like, you know, parents have a bunch of kids. Well, you got to have the parents before you have the kids, so you got to have the common function and the parent function before you have all these other ones that are created from manipulating the common function, the parent function. This common function is going to be y equals x squared. We already know what that looks like. I'm hoping we already know what that looks like. We're going through points 0, 0, 1, 1, 2, 2, negative 1, 1, negative, I said 2, 2, that's really bad, 2, 4, and negative 2, 4. Because I need to square, right? 3, 9, negative 3, 9, 4, 16, negative 4, 16. Doesn't matter whether my x is positive or negative because I'm squaring. Okay, that's this function right here, y equals x squared. Now we're going to do this r of x function. R of x is equal to negative x squared. And hopefully you guys get what negative x squared means. Negative x squared is negative xx. The square is only applying to the x. It's not negative x times negative x. If I wanted negative x multiplied by negative x, I would call that negative x quantity squared. These are two completely different things. A negative on the outside and a negative on the inside, two completely different things. With the negative on the inside, this negative will be squared because the square will apply to anything directly left of it. And left of this square is this closed set of parentheses, so you got to go to the open set, and then anything inside here is being squared. This is negative, one negative on the outside, and only the x gets squared. Make sure you understand the difference between those two concepts. All right, let's go ahead and graph this thing, see what we get. Let's do an input-output combination, and this is just r of x equals negative x squared. Pick any number you want. 0, good job. Okay, put a 0 in here. You square 0, you get 0. Put a negative sign on the outside of 0, you still get 0. So 0, 0 remains 0, 0. It's not moving. Let's put a 1 in here. If I put a 1 into this function, r of 1 will equal negative 1 squared. 1 squared is 1. Negative on the outside of it means negative 1. Okay, if you want, that's what that is. So 1 goes in and a negative 1 comes out, so therefore my input-output, 1, negative 1 is right here as my xy coordinate point. Let's pick a 2. Put a 2 into the function of r of x. put a 2 in here, then my 2 is the thing getting squared and the negative sign stays there. So I just have -4. So 2, -4. 1, 2, 1, 2, 3, 4. You might have an idea now how this original common function of y equals x squared is being transformed or moved to become this function. Let's try something over on the left side of the y-axis, like -1. Let's do that. So if I put a -1 in for my x in my function, let's see what's happening. -1 in here. And now the -1 is being squared. This negative times a negative is going to give you +1, and the negative is still sitting on the outside. Or if you will, there's 3 negatives. An odd number of negatives multiplied together always results in a negative answer. So you know you have a -1 coming out of the deal. -1, -1. You can try -2 if you want. Hopefully you'll tell me that you're going to get a -4. So -2, -4. And one thing I know about this function as well is that it's a quadratic. And the shape of all quadratic functions is a parabola. And parabolas are definitely symmetric over the axis of symmetry. And the vertex goes right through the axis of symmetry. So you can see that this parabola is definitely symmetric. I could fold it over the y-axis, which is nice, just like the original one was. All parabolas are symmetric, so maybe you saw me looking at the 2, -4 and kind of eyeballing it and how far to go over here. But if you're 2 units away from the y-axis in one direction, you're going to be 2 units away from the y-axis in the other direction. So can you tell me how the original y equals x squared quadratic parent function gets manipulated to become y equals -x squared, or r of x equals -x squared? Hopefully you'll tell me r of x equals -x squared is y equals x squared reflected. I don't want the word flipped. Flipped is not a mathematical word and I don't want to hear it. We are reflecting over the what? This time we're over the x-axis. I'm going to leave a blank here and you know what's going to go in there already, I hope. Over the x-axis. Now when you reflect over the x-axis, when you do this, the motion or the movement of all your points is an up-down movement. So we are reflecting vertically over the x-axis. Reflecting vertically over the x-axis. Alrighty. I'm going to go ahead and box this because this is my final answer with my graph here and my description. Try not to touch anything else as I label, but every once in a while, we're good. That's good enough. Okay. Alrighty. Let's talk about that word executed one more time while we're on here before we give the rule. I'm over here, and let's say that I put a -4 into my function. If I put a -4 into this q of x function, do I negate it first, or do I apply my common function first? So do I negate first, or do I square root first? And the answer to that should be that you negate first, before the common function is executed. If your change to the common function is happening before the common function is executed, you are changing your x's, which is why we are reflecting horizontally, because when you move horizontally, you change your x's. The x coordinate is the thing that gets moved. And you can see, like I said over here, I had the point 4,2 on the original function, on the original parent function, and now I have -4,2. So you see it's the x coordinate that changed from a +4 to a -4. And it says the x coordinate is going to change. So you're good to go with that. But remember that the common function here is the square root function, and that is being executed after you change your x. So change of x is happening in this case. Over here, my common function is the squaring concept. So with this particular function, r of x equals negative x squared, I square first and then apply the negative sign. This negative sign is applying after I execute the common function. Any change that occurs after you execute the common function occurs to the y coordinate. And if you look, this point, like up here, 2, 4, this point is getting reflected over the x-axis and becomes 2, -4. So which coordinate changed? It was the y coordinate that changed. And the y coordinate is changing because this change to the original common function took place after the common function was executed. Any changes that take place after the common function gets executed will affect the y coordinate only. Any changes that happen before the common function is executed will affect the x coordinate only. So let's make sure we have that concept. All right, so we're going to put a rule down. All right, and we're going to say that y equals f of negative x. You see this negative x matches this negative x over here, so I'm hitting this rule first. F of negative x is f of x what? What is happening to the common function here to make it become the new function that we graphed? And I hope you can say that it's being reflected horizontally over the y-axis. And that's what this rule says. Y equals f of negative x is f of x reflected, not flipped, horizontally over the y-axis. Okay? Be careful. I know when you think horizontal, you don't think y-axis, but remember when you reflect over the y-axis, it's a horizontal movement. So you are reflecting horizontally over the y-axis. I hope that makes good sense to you. Let's do another one. Y equals, this time the negative is going to be outside. Okay, so my common function is executed first, and then I negate. That's f of x reflected. Try not to just change the words from the one you had here, but try to think about it. This f of x is just like a y. And when you go negative y, right, aren't your positive y's up here and your negative y's are down here? So you're going from top to bottom, or in some cases bottom to top. You're reflecting vertically, up and down. Because the y value is the thing that is getting changed. And when you change only the y value, you move an up and down change. Y's move up and down, x's left and right. So negative f of x, and I don't want all this stuff in my rule by the time we're done looking at it, is f of x reflected vertically over the, if you're going to reflect vertically, you're going to be dropping over the x-axis. Okay. So these are 2 more rules. So now we have 6 rules altogether. Our first rule was shifting up vertically, shifting down vertically. That was our second rule. Shifting to the left, I believe it was, horizontally, and shifting to the right horizontally. And now we are reflecting horizontally over the y-axis and reflecting horizontally over the x-axis. We have 2 more rules coming up that deal with, well, I could actually call it 4 rules if I wanted to, but we have a rule with vertical stretching, a rule with vertical shrinking. And it's going to end up just being 1 rule, and I'm just going to combine it together. And then we have horizontal stretching and horizontal shrinking. All right? And we will deal with those in the next couple of videos. All right, I just want to make up 1 more example and see if you can tell me what it is, okay? So I'm going to erase these rules. Hopefully you have them. I'm going to erase these examples. Hopefully you have them. You know what? I think I'll leave that one. And let's just make up an extra.